All right, let's keep going with L'Hopital's rule. Well, one thing I want to mention is only use L'Hopital's rule when you have 0 over 0 or an infinity over infinity type limit. If you don't have one of those, L'Hopital's rule will mess things up. And I want to do an example like that. But this guy right here, x goes to 2 of this. On top, if you just plug the 2 in, up top you get 0, but on bottom you get 4. So the answer to this is just 0 over 4, which of course is 0. No L'Hopital required. But if you, maybe I should write this in red, if you used L'Hopital's rule, maybe I should say if you tried to use L'Hopital's rule here, which you absolutely should not do because this is not an indeterminate form, you get the wrong answer. And let me show you what would happen. If we did that, if we did by L'Hopital's rule, the top of this would become 2x minus 2, and the bottom would just become 1. And now I can plug my 2 in, and up top you get 2 times 2 is 4, minus 2 over 1 gives you 2, which is wrong. So, only use L'Hopital's rule when it's appropriate. And it's not appropriate here because this is not, our original limit here is not infinity over infinity or 0 over 0. All right, let's look at this next example. Sometimes you have to use L'Hopital's rule more than once. We've already seen that in one problem, but first let's look at this. As x goes to infinity, as x goes to infinity, the top of this goes to infinity, and so does the bottom. So we'll take the derivative of the top and bottom. The whole reason that L'Hopital's rule works is because both of these things are going to infinity, and it's really a question of which one's going faster. So taking the derivative means instead of comparing the function values, we're comparing the function's speed. So let's see a little bit of chain rule going on the bottom there. We get this. Now if you plug the infinity in, as x goes to infinity, this top bit also goes to infinity. And so does the bottom bit. So we got to use L'Hopital again. So let's see, on top we get 6x. On bottom, the derivative of that, let's see, the 1's going to go away. This, when we take the derivative, we'll get another factor of 2, so we'll get 4e to the 2x. And we still got infinity over infinity. Because x goes to infinity, both of those things go to infinity. So one more L'Hopital. And let's see, on top, the derivative of that is 6. On bottom, we get 8e to the 2x. And is this indeterminate? No, because the top is 6 and the bottom is infinity. So what you've got is finite number over an infinite. So this is going to be 0. And that's my answer. So sometimes you have to use it several times. Let's see, 117. Let's look at it. The limit is x goes to infinity. This time we got x natural log x over x squared plus x plus 1. When x goes to infinity, both of these guys go to infinity. So the top goes to infinity, the bottom goes to infinity. So by L'Hopital's rule, okay, the bottom is going to be nice and quick. The derivative of that's 2x plus 1. Now the top, let me rewrite that. It's a little more legibly. Now to do the derivative of the top, we've got x times natural log x. So we got to use the product rule. So we get first times derivative of the second plus second times derivative of the first. So the top is just 1 plus ln x. The bottom is 2x plus 1. All right, so as x goes to infinity, the bottom also grows to infinity, and the top grows to infinity. So we can use L'Hopital's rule one more time. All right, so we got limit as x goes to infinity. The derivative of the bottom is 2. The derivative of the top is going to be 0 plus 1 over x. All right, and now as x goes to infinity for this, the top is going to go to 0 because 1 over infinity, when x grows large, that goes to 0. And the bottom is just constant at 2. So this is going to be 0. All right, let's see this next one. I'm going to skip that one for right now because it's actually very similar to the limit we did there. So let's skip 1118. 1119, let's look at this one. This one's kind of interesting. On the top, you've got x to the 1000, and on the bottom, you've got e to the x. So both of those go to infinity. So we've got to use L'Hopital's rule. The derivative of e to the x is just e to the x. On the top, derivative of e to the 1000 is 1000 x to the 999. All right, this is still an infinity over infinity type. So we've got to use L'Hopital's rule again. So on the bottom, we've got e to the x. On top, we've got 1000 times 999 x to the 998. And so we have to use L'Hopital's rule one more time. Well, not just one more time. You know, when we use it, after we do it one more time, the bottom is going to remain the same. The top now is 1000 times 999 times 998 times x to the 997. So, I mean, really, what we'd have to do is use L'Hopital's rule like 1,000 times here in order to get this down into something that's no longer an infinity over infinity type. So let's just look at what's going on. I don't want to write out all the steps here because that would be insane. But let's think about it. I should probably put a dot, dot, dot here. Dot, dot, dot. After a bunch of these, what we're eventually going to have is 1,000 times 999 times yada, 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 3, 2, 1. Because notice what happens. Every time we go from one to the next, we get another number multiplied on the front, and this up here goes down by 1. So if we did this 1,000 times, we'd eventually have this. So we'd have x to the 0, we'd have all that, and we'd still just have e to the x down here. And I'm going to erase that x to the 0 because x to the 0 is just 1. And so we'd eventually get this. And this, the top is a finite number, although it is massive. It's a finite number, and the bottom is infinity. So finite, let's do that in green, finite number over infinity. So this is going to be 0. So that kind of leads us into this next idea here. The sort of takeaway from this is that this exponential is going to win against the polynomial there. So what we can do is we can sort of divide our functions up into different classes of function and see that like exponentials are always going to outrun polynomials. And this video is getting long, so I'll pick that topic up in the next video.